Hi everyone, welcome to my presentation titled Partial Binarization of Neural Networks for Budget-Aware Efficient Learning. I am Neeraj Anand. This is joint work done by Udbhav, Saksham, Dilip, and Deepak. There are several techniques to compress the over-parameterized neural networks like pruning, quantization, binarization, and knowledge distillation. Binarization is the extreme case of quantization and is powerful compression technique, significantly reducing floating point operations. In binarization, we scale down the 64-bit weight and activations into single bit. The most optimized way to do that is by using the sign function, which is demonstrated mathematically in figure 1 and graphically in figure 2, where the original convolution operation is replaced by XNOR operation, which significantly improves the computation time and it can lead up to 32 times memory saving. The main issue with this technique is that it often results in significant drop in model performance. To address this issue, partial binarization technique has been developed, but a systematic approach to mixing binary and full precision parameter in a single network is still lacking. To circumvent this issue outlined in the previous slide, we propose a controlled approach to partial binarization, creating a budgeted binary neural network B2NN shown in figure 3 with our novel MixBin strategy described more in the next slide. This method optimizes the mixing of binary and full precision components, allowing for explicit selection of the fraction of the network to remain binary. In figure 2, we see that when the B2NN is created using the mixed-bin strategy, it outperforms the other baselines explained on the later slides, and the performance is significantly better at lower budget. For example, at 10% of the floating point operations of full precision counterparts. Now coming to MixBin, MixBin is a search strategy to compress a given full precision network through partial binarization in an optimized sense. The inherent design of MixBin facilitates budgeted binarization, allowing to develop lightweight models that maximally exploit the available compute resources. Unlike greedy selection approach, MixBin identifies the set of layers to be binarized in one single pass, eliminating the requirement for any model update via backward propagation. It involves first calculation the binarization coefficient k with respect to every layer. To compute ki, only the ith layer is converted to binary and the performance of resultant network is computed. Here we presented two variations of MixBin that differ in how K is calculated. The first one is MixBin loss. This formulation assumes that if a specific layer is favored over the others for binarization, converting this layer from full precision to binary while maintaining all the other layers at full precision would result in minimal performance degradation. Based on this, K is calculated according to the first equation, and then it is sorted in ascending order, and the layers corresponding to first n, which depend on the budget, are chosen to be binarized. The second one is MixBin grad. This formulation is based on the hypothesis that beyond the drop in performance of the model, the inertness of the resultant network also plays an important role in deciding the importance of layer for binarization. Based on this, K is calculated here according to the second equation. Now, talking about the baselines, we show here the different baselines that we choose for comparison with MixBin. Random selection selects the layer randomly that should be binarized. Front BN chooses the layer from front and the rear one chooses the layer from the later part of the network. Iterative selection selects the layer iteratively one after other on the basis of its effect on network performance. In pseudo-random, after selection of layers using MixBin, we replace a subset of them from random layers. BNAS is based on the L2 difference between binary and full precision weights. Adaptive MBQ uses Taylor expansion. to build a metric for quantifying loss sensitivity. Hawk B2 uses the trace of Hessian metrics of each layer to identify the layers that are more sensitive to binarization, while network slimming is a pruning approach to create a compressed model. Now coming to the result, we show here results obtained during partial binarization of neural networks according to our MixBin and other popular baselines using ResNet 18, MobileNet on several datasets like CIFAR 100, TinyImageNet, and ImageNet 1000. We can see that how B2NN created using MixBin, outperform or the other baselines on even at lower buzzers. Like for example, ResNet 18 at the budget of 10%, there is a performance gain of 2 to 3% over the full binary neural networks, and at higher budget, it performs better than full precision counterparts. And across all the other budget, it outperform all the other baselines. We show here a comparison of accuracy of comparison of accuracy and flops for MixBin and other baselines on downstream tasks of lightweight object trackers shown in Figure 1, and in Figure 2 we show the transferability of B2NN model across the other data sets. In this regard, we present results from this scenario of model transfer from ImageNet 1K to Tiny ImageNet and CIFAR 100 dataset for object classification, and from ImageNet 1K to GOT 10K for object tracking. Clearly, B2NN designed for large datasets such as ImageNet seem to work well for the base datasets, thus do not require any additional layer selections. Uh, Now coming to conclusions and future work, MixBin creates compressed model that perform better on several data sets with several model choices, and our experiments show that B2NNs created using MixBin outperform those from random or iterative searches and state-of-the-art layer selection method by up to 3% on the ImageNet 1K dataset. We also saw that B2NNs outperform the structured pooling baseline by approximately 23% at the extreme flop budget of 15% and perform well in object tracking. And for future direction, there can be further investigation for partial binarization at more granular level, like at the channel level. Thank you.